Okay. I think I have the difficult duty of delaying your lunch a bit more. It's 12:30 already. Shall I squeeze a bit the presentation or using the full 45 minutes? Okay, good. So as you see, I've been pretty imaginative in terms of formulating a title for this series of lecture. The New Frontiers in Ocean Circulation Modeling is a series of lecture for the New Frontiers in Operational Oceanography International School. So I thought that maybe I could briefly let you know who I am, because I wasn't there on Monday and Tuesday. So just to let you know my contact details, I'm a physical oceanographer interested in ocean fine-scale processes. Mostly involved in modeling those ocean fine-scale processes and the scale interactions between those processes and the larger scales, say oceanic climatic functions. And I'm mostly working on the ocean, on the mid and high latitude physical processes. I'm involved in NEMO ocean model development in SWOT science team, in CLIVAR ocean model development panel, and quite excited about the questions related to open source, open data, and reproducibility in our field, and this large amount of data that we're now facing from satellites and models. Okay, so what we're going to discuss, we're going to have 3 lectures. Starting from very basic fundamentals and going to more, say, research-related questions. So the first one today, we'll be talking about the scope, usage, and fundamental principles underpinning ocean circulation models. We'll then tomorrow switch to, on Saturday, switch to the actual representation of physical processes in ocean circulation models. How do we deal with that? What does it mean? And lecture 3 will be more, say, blue sky research, and I'll try to explain what we believe in Grenoble is a vision of what could be ocean modeling in 10 or 20 years, so with more probabilistic and data-driven approaches to ocean modeling. So those lectures and the book and the associated book chapter are actually available on my GitHub page. I thought it might be interesting because obviously the topics we're going to cover here are that's huge. There are huge communities of people with different backgrounds working on that, a large number of issues. So we're only going to briefly flash a number of questions. If you want to get more deeply into understanding what we're talking about, I suggest those readings. And I'll be for the next next hour or so, I'll be assuming that we have a basic background and that you all know somehow what are ocean models, and I'll try to re-explain what are the fundamentals there. Okay. So first lecture today. So 40 minutes remaining for basically trying to define precisely what is an ocean model, what we use them for, trying to describe the physical hypotheses and the governing equations, and explain how we discretize them, and trying to highlight a couple of skills of current ocean circulation models. So because I'm a well-structured person, I thought that I should come with a clear outline. So the outline goes like this. We have 5 parts for today's lecture. We'll see how far we go and how good you will be with dealing with delaying the lunchtime. We might squeeze it a bit if we need it. So basically, scope, physical formulation, discretization, boundary conditions, and then skills. Okay? So let's start with the scope and the applications of ocean circulation models. So what is it we're talking about? We're talking about a branch of numerical modeling that deals with the representation of physical mechanisms that govern the evolution of ocean physical properties. We're talking about temperature, salinity, and current velocity. Seems easy, but if you think about that a bit more carefully, we're talking about representing a large variety of ocean processes. You surely know this diagram, and I could have picked up a number of them, but just consider how varied the number of physical processes we need to account for are. So we're not talking here about representing a 3D turbulence in a box. We're talking about a very complex system with very different flow regimes or occurring in different locations, situations, ranging from surface processes, processes in the bottom boundary layer, and there's a lot of physics there involved. If you want to really know what you're doing, you need to understand the physics. So first, large range of physical processes. And the point I'd like to make here is that there's no ocean circulation modeling without physical understanding of the physical processes. So understanding the physical processes is pivotal to our ocean circulation model. That's information number one. Now, try to think about the problem we're facing here. So you probably know this diagram too. This is all the range of, say, major ocean physical processes as represented in a time and space-time scale and space scale diagram by Dudley-Shelton. What you see here is that we have many things occurring in the ocean over a large range of spatial scale and a large range of time scales, with mostly interesting things are happening down to millimetric scale, okay, where we believe energy is being dissipated in the ocean. Say you want to really account for those scales in an ocean model, and just take a piece of paper and write a few numbers. If you really want to actually describe all the scales, you would need to deal with a number of parameters that's about 10,000 times larger than the Avogadro number. So we're talking huge numbers here. So basically, fundamentally, what I mean is that we're dealing with a truncated version of the evolution equations of the ocean state. So truncation and closure is also a fundamental and pivotal aspect of ocean circulation modeling. So first, we need to understand the physics. Second, we need to deal with closures. Okay, so we can now refine a bit more our definition of what an ocean model is. So basically, an ocean model deals with physical processes and physical properties over times and spatial scale of, say, global to kilometric scale, and time scales of, say, ranging from hours to decades. Okay, that's the current status of what we're able to do with those models. We need to account for cross-scale interactions, and uncertainty is really consubstantial. That's a complicated word. Consubstantial to ocean circulation modeling. Now, it's also a tool of choice for building a physical understanding, and this is why we're using ocean circulation models both in realistic settings and idealized settings. This is key, I think. Okay, so in practice, what is it we're talking about? So we're talking about a system that is providing an approximate solution to a set of PDE that describe ocean dynamics. This set of PDE obviously is inherited from the Navier-Stokes equation under a particular set of approximation adapted to the regimes we're dealing with. So we have also initial and boundary conditions so that we have a closed problem. And the first attempt for dealing with this problem goes back to the pioneering work by Brian, as mentioned by Eric earlier this morning. If you want to really be even more practical, what is it really we're talking about when we talk about ocean models? We're talking about codes, lines of code, something like 10,000 to 200,000 or 300,000 lines of codes, mostly in Fortran and C, that are basically run on supercomputers in HPC centers. And I'd like you to be aware of two things. The first is each of those codes is actually the result of a long-lasting effort by groups of people. So building any single ocean model requires 5 to 10 years of work within large teams. Okay. And if you want to further develop, maintain, and run your ocean circulation models, you actually need to have many people interacting together. You need collaborations to do this, and a collaboration among people from different fields and with very different skills. So basically, ocean numerical modeling is a group effort. Okay. I thought that maybe it would be interesting for you to get an idea of what is the current landscape of ocean circulation models. So it's a tentative list of currently running ocean circulation models that are, say, unique criteria for that sort of effort. So I tried to review recent literatures, and I'm only talking about currently developed, supported, or used models with publications about applications at global to basin scale over the last 5 years. So it's very possible that I've missed a number of models. So if you feel so, please don't shout too loud. Okay, and go back to me after break. Okay, so this is the list. So what you see is that there's a fair number of models coming from the US. There's a number of efforts coming from Europe, Germany, and EU in general, and a number of Asian models from Japan and emerging models from China. It's important to notice that we have here a variety of ocean circulation models that come from, that come with different, say, grids, vertical coordinates, and subgrid closures. It's important also to notice that most, if not all, not all, but almost all, are actually freely available and distributed under open source licenses, which is key to their usage in science. So that's a key aspect from my perspective. So what is it we use ocean models for? We use them simply for hindcasting ocean circulation. That's what we do when we run them with under prescribed atmospheric forcing. We're using them integrated with data assimilation for providing short-range ocean forecast and for ocean reanalysis. We use them coupled with atmospheric models for providing seasonal to decadal forecast. And when they are fully integrated in Earth system models, they are key to provide climate climate projections. Okay, and also one thing you also need to be aware is from the first. At a very basic level, ocean models are just a tool for testing ideas in order to understand how the ocean works. And that's again one point I'd like to make clear to this audience. Okay, obviously that's a large range of applications here, and all the models I've been mentioning previously, they are not all targeting this whole series of applications, apart maybe from NEMO, I guess, but all of them are, say, within this trend, this general trend of being, they should be able to do all this if they were putting the effort. So basically, there's this idea that the same ocean circulation models can be used for a wide range of applications over a very wide range of space and time scales. Okay. Why is it we're talking about ocean models here in this operational oceanography school? I guess for two reasons. The first is ocean models are a major component of modern operational oceanography. You obviously know that they are used for as building blocks in forecasting systems. Basically, what they do, what we use ocean model for, is for extrapolating in space and time the information, the incomplete information we have from observations. And the way how we want to do that is by using, say, first principle physics for constraining a physically consistent estimate of the ocean state and of its evolution. One thing you might not be that aware of is the fact that we also use ocean models for preparing future oceanic observations, either from satellites or from in situ networks. So they are routinely used for observing system experiments too. So that was point one. Point two is you need to be also aware that there's an intricate and intrinsically interrelated connection between satellite remote sensing and ocean circulation modeling. First, they have emerged over the last 30 years with a very interrelated history. And if you're fair, you can see that the actual resolution of global ocean models has followed the evolution of satellite altimetry over the last 30 years. And to a large extent, altimetry provides a target for advancing ocean models. In return, ocean models are used for preparing satellite missions. So that's also one of the reasons why we're talking about ocean models here. Not only because they are building blocks of the systems, but also because they are pivotal to basically a lot of activities connected to operational oceanography. Okay, so this was part one. How am I doing with time? I'm drifting also. Okay, physical formulation. Talking about things you probably all know here, so I'll be quick. So we're talking about approximating the Navier-Stokes equation. So we need to define precisely what sort of approximation we're going to make, because integrating the full Navier-Stokes equation is out of reach. So what we do is a set of, say, common approximations that are pretty much shared by all the ocean models. So first, we're assuming that the Earth is round. It doesn't mean that gravity may not change with space, which we're assuming that the geometry is round. That's not too bad an approximation. I don't think we actually know how bad an approximation that is. Okay, we're also assuming that the ocean is thin. Okay, the fact that the ocean is thin implies that you can assume that the rotation rate doesn't change with with depth, and therefore you can neglect a number of terms in the Coriolis force. So that's good for simplifying your equations. We're also making this turbulent closure hypothesis that tells you that whatever the scale you're going to discretize your model at, you're assuming that you will be able to infer the effect of the unresolved scales on the large scale from knowledge of the large scales only. That's a very strong hypothesis, and to a large extent unsupported by first principles. Okay, so that's a major hypothesis we have here. Most ocean models, but not all, are using the Booth-Nares hypothesis, where basically we neglect the variations of relative density in some terms in the momentum equation, and don't want to get in detail there, but this is not so important. Some models actually are not using it anymore. We're using the hydrostatic approximation. That allows us to actually neglect vertical acceleration. Therefore, W becomes a diagnostic variable, and this allows to use larger time steps basically in the models. But some codes are actually relaxing this hypothesis, and it's very likely that over the next 10 to 15 years we'll be thinking about how to integrate those in operational oceanography centers. And there's the incompressibility hypothesis, where basically we assume that the sound waves are propagating infinitely fast, and therefore this also allows us not to represent them, and therefore to use longer time steps. So you all know that. So in the end, what you get is the set of primitive equations with this horizontal momentum equation, the hydrostatic equation, the incompressibility equation, conservation of heat and salt. There are extra information you need to put in so that you get a closed problem. First, you need an equation of state. So I said conservation of heat and salt. I should be more precise here. We're talking about conservative temperature and absolute salinity as defined with the TOS10 equation of state. So basically, the relative density is a function of temperature, salinity, pressure. You need to be aware that this relation is nonlinear, and the more nonlinear when you get to cold temperature and to high pressures. And it has a number of implications for ocean dynamics, especially at high latitude and in the deep ocean. Okay. The second additional information you need to bring is your boundary conditions. So I'm only here describing the surface boundary conditions, but you also have boundary conditions at the bottom and on the side. So there's a kinetic boundary condition that tells you that your free surface, that the surface is evolving in time. So there's an equation for this. Previous generation ocean model were just assuming that there's a rigid lid on the top of the ocean. It's no longer the case in most models now. There's a condition for the pressure at the surface. In most models now, this condition is prescribed with time and spatially varying fields. There are RC fluxes of heat and salt, and we'll go back to that later. And there are fluxes of momentum, and basically what this equation tells you is that the actual momentum is being transferred and varies continuously across this continuum from the atmospheric boundary layer to the ocean boundary layer. Okay, so those are the equations we're trying to solve in ocean circulation models. Okay, so how do we do that in practice when it comes to the discrete version of those equations? I'm not doing too bad with time now. Good. So basically, the idea is the following. Well, we're going to chunk the ocean in boxes, okay? And all those boxes are going to exchange information with the neighboring boxes, and those exchanges will be sufficient for us to infer what is the evolution of the properties within the boxes, okay? So if you want to do that, you first need to define your boxes. So it comes to a problem of spatial discretization. You need basically a grid for approximating your continuous variable in some sort of discrete space. So the simplest space you could think of is just square boxes. Okay, so that's latitude, longitude, and depth translated in a numerical space. That's I, J, and K, and you have boxes there. Okay, defined by their extension in the zonal, meridional, and vertical direction. This is highly simplified and probably not representative of what we actually do in real ocean circulation models today. And you need to be aware that there are a large number of grids that you can define and use in ocean circulation models, and a number of different approaches for defining those local approximations to continuous variables on those grids. Okay, so there's a whole field and a whole community of people working on this. Second, you need a temporal discretization. So you need to know how knowledge of the discrete variable would allow you to actually infer the evolution of the variables in time. So for this, basically you have your u, v, w, tsp at time t, and you want to infer what they will be at time t plus dt. That's once again a simplification. In practice, it's more complicated than that. But basically, you're always dealing with this idea that you have a full, say, continuous solution, an analytical solution you want to approximate, and you have a discrete estimate of it. Okay, this discrete estimate is imperfect. There are errors, and those errors are most likely a function of your grid spacing. Okay, so that's basic kind of information we're talking about here. Okay, so now, how can you be sure that the way how you discretize your equation will actually allow that if you increase the resolution, you will actually converge to the right solutions? There are a number of conditions there for this to be effective. The first is you want convergence. So basically, you want to be able to prove that your approximate difference equation will actually converge towards the actual solution of the partial differential equations you're trying to approximate when dx and dt are going to 0. Okay, so that's a condition, and you can formulate that mathematically and transfer that in terms of theorems and proofs for your numerical discretization schemes. Second, you want consistency. So consistency means that not only the solution should converge towards the solution, but the actual set of equations should converge in some functional space towards the actual continuous equations. Okay, and you want this to be true when you homogeneously decrease dx and dt. Okay, so that's consistency. It's key because not only you want your approximation to be good at a particular spatial scale, but you want this to be also true at another spatial scale. So consistency is key and slightly difficult to understand, I guess. Okay, and most importantly, you want stability. So basically, you want to be able to prove that there's an upper limit to the growth of your errors over time. And this actually translates into very practical conditions that relate, for instance, your time step to your horizontal discretization. Okay, so basically, the thinner your horizontal grid, the smaller your time step for the scheme to be stable. Okay. I thought that maybe I could just illustrate one aspect, one particular property of numerical discretization schemes. I mean, people are spending their life designing schemes, so it's not in 10 minutes that we'll be able to actually grasp real key issues there. But just for you to know that there are a number of notions that are key, I just decided to illustrate the question of the order of accuracy of discretization schemes. So assume you're able to refine, because you have a big computer, you're able to refine your spatial or temporal resolution by a factor 2. So you're changing delta x into delta x over 2 and delta t into delta t over 2. So the order of accuracy of your discretization schemes actually tells you about how, if you change your resolution, how the error per time step will actually change. So in practice, with the first order scheme, what you would have if I decrease my resolution, if I increase my resolution by a factor 2, I will decrease my error by a factor 2. And if I'm using a second order scheme, if I increase my resolution by a factor 2, I will decrease my error by a factor 4. And the more so when you get to high order schemes. So you can prove that mathematically for a number of schemes, and be really aware that we're not talking about the actual error here, but just the way how it varies with resolution. Okay? And obviously, what you can get from that is that at some stage, starting at a particular resolution, it might be interesting to actually use high-order scheme instead of increasing your resolution. Okay? But obviously, this comes with a price. The price is first that your higher order schemes are usually more expensive to run because they use larger mantises, so they imply a larger flow of data. And also, the boundary conditions are more difficult to formulate for those schemes. Okay? But the general trend in ocean modeling right now is to go towards high order schemes. Okay? That's just why I'm talking about this here. Okay, boundary forcing, before we switch to nice animations and lunchtime. Boundary forcing. So I think it's probably important that you're aware that we're talking about a forced dissipative system here. So the main forcing of ocean circulation is due to the momentum and buoyancy exchanges with the atmosphere. They are basically drivers of the horizontal and vertical circulation in the ocean. There are obviously additional influences coming from, say, exchange of fresh water with rivers, exchange of fresh water and heat with sea ice, exchange of fresh water and heat with continental glaciers. I mean, those are, say, additional forcings, but the main forcings is momentum and buoyancy over the open ocean. Now, we put energy and stuff in the ocean. It has to go somewhere. And this somewhere is generally speaking when you talk about energy at small scale. So basically, at small spatial scale, energy is being converted to heat in the ocean. Okay, so we have here an engine. You put energy in, and it dissipates the energy. So we're not talking about a system that is closed. We're talking about an open system that is forced and dissipative, which means that the way how you specify the forcing and the way how you specify the mechanical energy dissipation in your model is key to the solution you would get. Okay, the long term. I mean, if you're talking long term climate projection, probably one of the key aspects in terms of the ocean representation there is how we dissipate the energy, because the whole trajectory of your model would depend on that. Okay, so forced dissipative system means that we not only need to care about the kernel, the dynamics, but also about the information we put in and how we extract the energy from the model. So how is it we impose the forcing? It's probably interesting for you just to be aware of the actual time scales of atmospheric forcing, because it's the main driver. So we're talking about variations over the diurnal cycle, variations at synoptic time scales. We're talking about the seasonal cycle. We're talking about the interannual fluctuations, and just an illustration for you to be aware of the problem we're facing here. You have here an illustration of the curl of surface currents in the ocean on the left and curl of surface winds at the base of the atmosphere on the right. And this comes from a high-resolution couple simulation performed with NEMO and IFS quite recently by Laurent Brodeau, I think. And what you see here is that the actual spatial and time scale of what's happening in the atmosphere is very different to what's happening in the ocean. So we're talking in the atmosphere about large things moving fast, and in the ocean small things moving slowly. Okay, so in practice, what it implies is that you need to actually impose forcings at very high frequency from the atmosphere to the ocean, or to exchange information at very high frequency between your atmospheric model and your ocean. Okay, so time scales there. How do you do that? So there are two different ways to do that, depending on whether we're talking coupled models or forced models. Pivotal to this is the notion of bulk formula. So we're talking about the green box here. This is the function that, given atmospheric variable and ocean variable, would give you the actual fluxes. The fluxes, and this is a very weakly constrained component of an ocean circulation models. So if you're in a couple model, basically you will exchange information between the atmosphere and the ocean through this bulk formula for what concerns the evaporation and the turbulent fluxes. And if you're in a forced model, then you will use satellite data for constraining the radiative budget, and fields coming from reanalysis or analysis for constraining, say, the temperature, humidity, and velocity in the atmosphere, therefore being able to compute precipitation, runoffs, radiation, and blah, blah, blah. One thing that is also important, and it maybe relates a bit to the talk by Tonelli an hour ago, is this idea that within a forced model we need to use some ad hoc representation of a missing feedback from precipitation. I mean, from evaporation onto precipitation. So that's what we call the sea surface salinity restoring. Okay, just for the sake of illustration, it's not only it's not only air sea fluxes over the ocean that we need to, over the open ocean that we need to care about. There are also a large number of, say, details that you need to care about. And those details may actually have a very strong influence on the solutions you have. I'm just here illustrating recent works we've been doing in Grenoble as to improving the way how we deal with Antarctic freshwater fluxes in ocean models. So basically, you all know that there are ice shelves around Antarctica, and that there's a circulation under those ice shelves, and that this circulation is changing, and that there are questions as to how those changes are affecting ocean properties, and the first of them is the extent of sea ice. Okay, so just to give you an idea of what we're doing, ocean models are a mixture of very high-end mathematics and understanding of the physics, and very crude representation of things we don't pretty much know. So just to get a look, here is the way how we previously were representing those freshwater fluxes from ice shelf in NEMO, and I think it's pretty much in phase with all the ocean models except for MOM at the moment. So basically, an evenly distributed flow of fresh water put at the surface and vaguely constrained by observations. Now, what we're doing with NEMO is that we're using an observation constraint, a map of calving and basal met. We're using a Lagrangian iceberg model. We're using a particular parameterization of the flow under the ice shelf cavities. We're even describing the flow under the ice shelf cavities. That's a lot of work. And that's certainly something that is not really well constrained. So the point I wanted to make is that the forcing function in ocean model is key. It requires a lot of efforts, and most of the time very crude approximations. Okay, good. I wanted to highlight a number of caveats of this representation of air sea forcing and forcing functions in ocean circulation models, because I think this is a very much. Those might be a number of questions on which some of you might be working on in the future, and it's probably fair to expect that future satellite observation will probably change the statements I'm expressing here. So the first is we have large uncertainty in air temperature, specific humidity, and winds as obtained from reanalysis, and that's especially true at high latitudes. The second is even with the most high-end atmospheric reanalysis, we're basically there in the range of, say, 5 to 10 kilometer resolution. But as I will show in a couple of minutes, we're running ocean models at, say, kilometer scale. So we still have a mismatch between the information we have for forcing the models and the actual resolution of the models. As I was saying earlier, the bulk formulae are very weakly constrained. So if you really look at the core papers, at the basic papers that underline, that supports the formulation of those formula, you're just afraid to see that it's a handful set of say Bohr measurements, because you need to measure ocean properties, atmospheric boundary layer properties. It's not an easy business, but basically those formula is calibrated onto, say, probably less than 100 data points. Okay. Well, data times series, I should say. But most of them are representative of the quiet ocean at mid-latitudes, basically where it was possible to go and put buoys. Okay, buoys. So basically, they are probably very well off in the Southern Ocean and at high latitude, and we don't know how to deal with that. As I was saying earlier, there's this missing feedbacks from evaporation onto precipitation, and therefore there are tricks for dealing with that. But that's a fundamental, say, inconsistency in the formulation of ocean models. There's also this question of the phase mismatch between the observed fields that are actually the atmospheric fields that are influenced by the ocean properties at fine scales in particular, and if you run a free run model without that assimilation, then your ocean properties will not have the same phase, and therefore you're forcing a model with information that's inconsistent with the actual state that is there in the ocean model. So it might be an issue, and especially when you come to very high resolution, where we know that there are strong couplings between the atmospheric dynamics and the ocean dynamics in the atmospheric boundary layer. So basically, we know that we're missing a number of feedbacks from the ocean state onto atmospheric properties, in particular in forced ocean model, and this is certainly one thing that will attract a lot of attention in the near future. Okay. So this was for the, say, equations and presentations. Now we're going to the more relaxing phase of the talk, showing pretty pictures and movies. Okay. Okay. So this so I'm just trying to illustrate here a number of skills of current ocean models. So first, we're talking about global mesoscale permitting ocean circulation models. So here is an illustration of surface currents in, it's actually from the same simulation that the one I was showing earlier. So we here have the surface currents, so that is the norm of the surface currents in meter per second, in this simulation where NEMO 1/12 of a degree have been coupled to IFS at quite a high resolution too. So what you see here is, well, okay, a wealth of scales in the ocean. And this is true for NEMO, but this is also true for other ocean models. What you see here is a pretty similarly the same kind of information with probably a nicer layout. They probably have a nice graphic and computer people there at NASA. It's from ECO. So what you see here is once again the norm of surface currents and its evolution over time. So you see that we're now able with those models to represent a very vast variety of scales. Okay, and you can spend hours just describing some of the dynamics you see here. If you're interested in specific region, you can zoom in. I mean, it's one thing that you should try and avoid when you're an ocean numerical modeler, not to spend too much time watching a movie. You could spend your whole day doing this. Okay, so going back to this, so this is for the illustration, but you can also be a bit more quantitative there. And well, this is one of the many illustrations that you could get, showing that there's a fair agreement between altimetry and this generation of, say, eddy permitting global mesoscale resolving or mesoscale permitting models, say with grid resolution of about 10 kilometers. They are generally able to describe the mesoscale variability as we observe it from current altimetry. So basically here that's an illustration of what you get in terms of surface height variance from altimetry over 2 years. That's from a joint product, I think, and what you get in one of the earliest NEMO OCO 12 simulations. So there are differences there, and if you're an ocean modeler, you could spend hours discussing whether those differences are important, blah, 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 blah. But broadly, the picture is there, the locations are okay, and the amplitude is okay. Okay. It's important to recognize that this is due, I mean, this is something pretty new. I mean, 10 or say 15 years ago it was not the case, because basically one thing has changed over the last 15 years. It's that we've been through some sort of a regime shift from ocean models with grid resolution of about 100 kilometers. That's where we were in the early 2000s, and where we are now with ocean models at global scale in the range of 10 kilometer resolution. Between the two, what basically happens is that you're crossing the deformation radius over a large fraction of the ocean. So basically, your ocean model becomes able to represent some sort of bioclinic instability. Obviously, it's probably not at the right scales. It's probably not as intense as it should be, but generally speaking, you're getting to a regime where you have fluctuations in your model. You're switching from laminar to a turbulent ocean modeling. So what you see here is EKE from Maviso, from 1/4 of a degree ocean models and from 1 degree ocean models, and you see that arguably the second map is closer to the first than the third is to the first. Okay, and you may read there are probably hundreds of papers showing the same kind of maps there. This was the big thing in the 2000s. Okay, now just a couple of illustrations about where we are. I mean, the new things. The new thing is probably the emergence of some mesoscale permitting ocean modeling at global scale, and that's certainly something that will emerge and become more and more important over the next years, and that's why I think it's worth illustrating here. So we've been knowing for quite a while. I mean, the first realistic simulations of the mesoscale flow go back to the early 2000s, and we know that when you get to higher resolution, those models with that particular formulation I've been describing this morning are able to describe those very intense fronts that we know are occurring at some mesoscale. So that's just an illustration coming here from one of the earlier simulations we did in Grenoble a couple of years ago. So basically showing that we have strong gradients of buoyancy at the surface when we get to, say, higher resolution. So we're here talking about 1/36 of degree simulation over the South Indian Ocean. Okay, this was a couple of years ago, or actually 7 years ago. Now we're there in a situation where we're able to run, say, basin scale, and some groups are even running global scale models that describe flows down to kilometric scale. Okay, so this is this goes along the presentation by Eric this morning, but basically the take-home message here is that we have the computing resources for running those models now, and we have a number of observations that can be used for actually assessing how good we're doing in terms of representing those scales. And what is for sure is that this particular formulation of model that was proposed 40 years ago, it's actually able to quantitatively describe the evolution of flows in very high Rossby number regimes, okay? In particular at the surface. So that's what we see here, see a handful of fronts and stuff. Interestingly, as mentioned by Rosemary yesterday, today, it's pretty much at the same time that those models, so basically those models, the first models that were actually able to reproduce at the basin scale, sub-mesoscale features, they are probably 4 or 5 years old at most, and one of the first information that we're able to provide is this very strong seasonality of sub-mesoscale flows. So here you have surface, you have relative vorticity in the near surface layers in winter and in summer. So one of the first signals that we saw with this generation of model is this very strong fluctuation that has implications in terms of kinetic energy spectra as diagnosed from altimetry. But because we were not aware of the fact that there was such a fluctuation in activity at small scale, there was no actual processing from observational data that was actually illustrating this. So basically, this has motivated a number of studies, and we now know that there's a strong seasonality of small balanced turbulence in the ocean. Okay, so that's one thing that ocean models have brought to this field. And the last illustration I'd like to raise is this. It's supposed to be movies, but for some reason I haven't managed to introduce them. But basically, what you see here is just cross-section of zonal velocity from that simulation I was showing a bit earlier. So you could easily convince yourself that it's not only balanced 2D turbulence that we're seeing in those simulations, because here we're using a large number of vertical levels, so 300 vertical levels. We're able to actually describe the actual generation and propagation of a fraction of the internal wave spectrum. And you may see here on this at certain location there that we have actually signatures of internal waves in those models, and signature of their emission in interaction with the bathymetry. So we're there at a stage where our models that were actually designed for describing, say, balanced flow at large scales are now getting into resolving a fraction of the internal wave spectrum. And how we're going to deal with that, how we're going to actually consider that there's energy there and that therefore we should not put it in subgrid scale closure is certainly an issue that will emerge over the next years. Okay, now wrapping up. We've been discussing about the scope, the usage, and the fundamentals of ocean circulation models. And I think I've tried to convince you that ocean circulation models are pretendedly based on first order, on first principle physics. It's not, we're trying, but there are things that are not as clear as we wish they would. Do you agree, Baylor? Yes, you do. We're using them for a wide range of applications, okay? And this is certainly going far beyond what the earlier explorers of, the pioneers in ocean modeling were probably not able to imagine how wide the range of application we have right now with those models. The more so, they are actually now building blocks and key building blocks of operational oceanography. I've tried to illustrate that. And most importantly, from my perspective, we're talking about group efforts and collaboration that requires long-standing investments of groups. So that's not an easy business we're talking about here. Okay, on the more say, scientific level, we've learned a couple of things. First, that subgrid closures are rate-controlling components of ocean circulation models. We've learned, or at least I've tried to illustrate and convince you that numerical discretization is a key aspect of ocean circulation modeling. but it's not all the story. Besides the kernel, there's also the interfaces, and this is not as exciting, but certainly as important in terms of constraining the solutions. And ocean models are now arguably able to describe acceptably well the mesoscales at global scale. And the new frontier we're facing now is the emergence of submesoscale permitting modeling at global scale. And I thank you for your attention.
Thank you, Julien. Questions?
You all want to go and have lunch, right? This one there.
Thank you for the interesting talk, first of all. And second, you said that all the ocean variability in the ocean comes from the forcing from the atmosphere. But what would happen with the ocean variability and the different scales of the ocean variability if there wouldn't be no forcing from the atmosphere, neither high frequency or long-term forcing?
That's a very good introduction to my third lecture. Thank you for this. I think it's probably fair to say that there's some sort of a paradigm shift happening right now in physical oceanography. Up to quite recently, it was accepted, say that over short timescales, say timescales up to decades, the atmosphere was driving the ocean. But when you were going to longer timescales, then the ocean was driving the atmosphere. And the emergence of those ocean models able to describe mesoscales at global scale has actually highlighted how important mesoscale can actually be in governing and in driving an intrinsic variability within the ocean that can actually impact ocean variables up to scales of a decade also. So basically, the short answer is a fraction of oceanic variability at time scales from month to decade is also due to intrinsic ocean motions, and I try to illustrate that during my third lecture.
Any other questions?
Julien, you made a good point for the link between improving horizontal spatial resolution and temporal resolution. Can you say a word about the link for vertical resolution and how to choose your vertical layers?
We actually had a chat about that with Baylor yesterday, and we pretty much agreed that there are a number of hand-waving arguments about how you should pick up your vertical resolution for a given horizontal resolution. There are a number of lines of thinking, so there are scaling with stratification, F, and the typical length scale you're looking at. You could also come out with rationale, say, wanting to describe this surface intensified dynamic that is acceptably described by the surface quasi-geostrophic equations, where you have a formal relation between your horizontal scale and vertical scale. But the truth is, there's no rationale there. It's more practice. It's, yeah. But that's a key constraint, and there's an issue when it comes to the design of operational system. It's far more sexy for an operational sensor to actually double its horizontal resolution than increasing its vertical resolution. So certainly over the next years, we'll have to understand much better the impact of vertical resolution, when it matters and why it matters, and in those compromises that govern the actual choices for the evolution of operational systems, the question of putting resources on the vertical resolution will certainly have to be considered.
Okay, one more.
Just a quick follow-up on that. One of the things that I think will be really interesting is when we try to get consistent with SWOT, and I think that will have a lot to say about what the vertical resolution has to be.
Okay.
I agree.